I'll now introduce the next speaker, who is Tony Heagerty. He's a fellow of the Academy of Medical Science and a professor of medicine. He's head of the Division of Cardiovascular Sciences, and he's an international authority on high blood pressure. This area is interesting because he's covering the cardiovascular and obesity immunology, which is an emerging area that's very much part of our focus on multimorbidities. These two areas are critically linked, and it's something that the Institute will be evolving over time. So,
well, Tracy, ladies and gentlemen, first of all, I'd like to say how nice it is to see so many of you whom I normally see over the table in the consulting rooms, and that you're all well. At least I hope you are. I also should say that all of you are going to die. And a lot of you are going to die of cardiovascular disease. I'll do my best. Now, what you're going to see is my take on what Tracy has kindly done for me in terms of an introduction. I should add that my comments are more germane if you are overweight, because that also reduces life expectancy. And what I'm going to try and do is walk you through why immunology and inflammation is going to become extremely important in terms of innovation and therapeutics for overweight patients that are reaching epidemic proportions in acculturated societies, so much so that life expectancy is plateauing in the United Kingdom currently. So just to put the clinical problem from a clinician scientist into perspective, the International Obesity Task Force, nearly 10 years ago, estimated that nearly 500 million adults were obese, and that was contributing more than 2.5 million deaths a year. And the principal cardiovascular phenotype is one of being overweight leading to high blood pressure, which about 37% of you have, dyslipidemia, which about 40% of you have, and diabetes mellitus, which I'm not certain about in terms of the phenotype in the room, but in a UK perspective, about 20% of obese people are going to develop, and even more as they grow older. And if you throw into the mix that there are obesity-associated cancers, you have a very real problem in terms of paying into your Christmas club. So, why have I introduced this concept? This is a 3D stacked electron micrograph of a small blood vessel, about 150 microns in internal diameter, and you can see the red blood cells here. And you can see that around the majority of these blood vessels, there will be a layer of fat. And these adipocytes are not just energy stores, they are also highly metabolically active. And it's not beyond the wit of man to suggest that some of these things that are coming out of these cells could have an impact on vascular tone. So, for example, if you vasoconstricted these blood vessels, your blood pressure will go up and your ability to unload nutrients into vital tissues will be diminished. Down here, you can see John Yudkin's hypothesis published in The Lancet in 2005 that vasocrine signaling from this so-called perivascular fat is the mechanism linking insulin resistance to vascular disease. So let's look at the methodology very briefly. If you want to do human work, you can biopsy this area of the anatomy, and you can take out a small biopsy of skin and subcutaneous fat. Now, the reason why this is so attractive is because the no, Tracy, there's not a need for that. Is the fact that it does leave a small linear scar which fades after about 6 months. But it allows you to take out these small blood vessels, and you can put them in organ baths, and you can leave the fat on, or you can take it off, or you can even return it into the organ bath so that you can look at whether it's working in a pro-favorable effect or a pathological effect. So let's have a look at what we've got. The first thing is, does this fat influence vascular tone? So this is the blood vessel in the organ bath, and it's been challenged with noradrenaline, and you go from left to right, you see this dose-dependent contraction. And this is a blood vessel without any fat on it. But if you leave the fat on, the vessel doesn't contract as well. It actually relaxes to a certain degree. And so we can conclude from our human studies of healthy volunteers that the healthy perivascular fat has an anticontractile effect. So what is being released in response to this spasmogen noradrenaline in a healthy context? And it's become clear that the majority of the anticontractile effect is attributable to this vasodilator adipokine adiponectin. You can see here, this is a blood vessel which has been left with its fat on contracting, and if you take the fat, if you challenge the vessel with a soluble fragment of the type 1 adiponectin receptor, which will mop up any adiponectin released, you see that the vessel contracts more, so the anticontractile effect has been lost. And then if you take the fat off, you can see that the anticontractile effect absolutely overlaps what you see if you put in the soluble receptor. So we're pretty certain that adiponectin is coming out of these cells. Now, what happens if you gain weight? Well, here are the results from a medical student summer project where he looked at the cells from lean volunteers and people with obesity. And you can see that we can quantify this. There is an increase in cross-sectional area, and that means that the fat cells get large and hypertrophied. There is also evidence from this dark black staining, which is for the TNF receptor 1, that there is inflammation. And all of a sudden, immunology becomes central to this story. From other data, not from our laboratory at this stage, but we have got data now, we know that there is also intense macrophage activation. So we know that metabolic syndrome, these are the patients with glucose intolerance and high blood pressure and dyslipidemia, they have increased inflammation and macrophages in these fat depots. Now let's look at what happens to the anticontractile effect. And here you see it doesn't matter if you leave the fat on or take it off in yellow, the dose-response curves now overlap. So the anticontractile effect has disappeared. So what do we have in the way of data with regard to the crucial roles of these cells? I'm just going to touch on the role of the macrophage because that's quite important. And these data could not have been accomplished without an interaction with Catherine Else's group, which was crucial. And I think the immunology links will become invaluable in unraveling this story in more depth. What you can see here is, again, this absolutely typical curve where if you leave the fat on the blood vessel, it doesn't constrict as much. If you then render the fat hypoxic, you lose the anticontractile effect. So now we have an in vitro laboratory-based model of obesity which can be accomplished in 3 hours. So hypoxia does mimic what we see in obesity. So then what we need is a macrophage deficient mouse. And what you can see here is what happens if you inject a wild-type mouse with diphtheria toxin. You see this spike in macrophages. But if you look in D, if you have a conditional knockout mouse with no macrophages, when you inject the diphtheria toxin, you actually don't see a macrophage activation surge. So let's look at the anticontractile effect. Here you have, with the fat on, you take the fat off and the blood vessel constricts more. But if you leave the fat on and you have no macrophages, there is no loss of the anticontractile effect. So the macrophage is crucial for the loss of anticontractile activity. So then the story becomes even more complex, and this is the subject of our poster outside, because the inflammatory and immunological aspects of this work in obesity are largely owned by Dr. Withers in the University of Salford, with whom we closely interact. But this paper was published in Science from A.J. Chowla's group in 2011. And this is, again, why we need Richard Grensis and Catherine Else to play this game in more detail and have some more fun. Now, what they found was that if you put a mouse on a high-fat diet, it develops increased body fat and it becomes diabetic. And there are no eosinophils taken up by the perivascular adipose tissue depots. But if you then parasitize the animal and induce eosinophilia, you protect against diabetes. And Richard recently suggested that we injected mice with IL-33, and actually we could also cure diabetes by promoting an intense eosinophilia, and that's the subject of the posters outside. So if I summarize what I want to say and then move back into how we might make healthy people, fat people, healthy, this is how we are born, the majority of us, and how we want to regard ourselves throughout our lives, thin and pencil-like with healthy fat. But we get globular, and our fat cells get large, and they become inflamed. And when there is inflammation, there is loss of perivascular adipose tissue anticontractile function, so basal vascular tone goes up. Peripheral resistance will go up. There will be decreased exposure of triglycerides to endothelial lipoprotein lipase, and there will be decreased nutritive flow, which will mean blood pressure, dyslipidemia, and insulin resistance, and the metabolic syndrome. In other words, what we have is a proof that John Yudkin's hypothesis was correct, which is not bad for an Arsenal supporter. So let's look quickly now at what we can do for people who are overweight. This is an experiment in obese mice. So if you feed a mouse a high-fat diet, 60% fat, it becomes overweight. Its systolic and diastolic blood pressure goes up. Its glucose goes up, its insulin goes up, and its noradrenaline levels go down. There is autonomic dysfunction. And what you can see in terms of if you exercise these mice, which is interesting, you can put them in a swimming pool and you prod them with a stick because otherwise they just float around happily in the swimming pool. They actually plateau in terms of weight, but they don't lose any weight. So they remain obese. That's the key point. But the blood pressure comes down in blue, both systolic and diastolic. The diabetes disappears as well. This is the blood sugar over here, and this is the insulin levels. And you can see that that autonomic dysfunction is restored. Now let's have a look at the fat. What you can see here is healthy fat. There is inflammation, and that's what exercise does. So the strain intensity for inflammation diminishes. And if we look at the anticontractile effect, there is an anticontractile effect as a result of exercise. So we have made these fat mice healthy in terms of vascular function and metabolic syndrome. And let's move it back into the human context, because these are quite dramatic data. There's a weight-reducing surgery program in Salford, and we know from long-term follow-up of weight-reducing interventions that there is a significant and sustained weight loss which cures diabetes and hypertension, prolongs life, so you better hang on to that, and halves cancer rates. bypass surgery is actually conducted in Manchester. So these are our findings. So what we have are some healthy volunteers. I'll go through these in detail in a minute. And then we have obese patients before their surgery and then 6 months afterwards. So you can see that at 6 months there is a reduction in waist circumference, a reduction in body mass index, but this is the key point. These patients, by definition, have a BMI above 35, so they remain morbidly obese. Their blood pressure, however, has been restored to normality. And if we look at inflammation in the bloodstream, you can see that high-sensitive CRP is reduced, IL-6 is reduced, TNF-alpha is reduced, although it's still quite high. Adiponectin levels, that key hormone in the blood, actually restored to completely normal, insulin halved, glucose now normal, and HOMA index dramatically reduced. So what happens to the fat around the blood vessels? Here is the fat and the TNF staining before and 6 months later. You can see the fat cells have reduced in size. So the area goes down, the inflammation goes down, and the macrophage numbers go down. And this is what you see when you look at the vascular tone. So this is what I showed you in the obese panel. There is no anticontractile effect because there's no adiponectin emerging from these fat depots. But after 6 months, you can see in blue the anticontractile effect has been completely restored and now overlaps the anticontractile effect seen in lean volunteers. In other words, we've made these obese people healthy, despite the fact that they retain morbid obesity. Their diabetes has gone and their blood pressure has been restored to normal. So in summary, you can see this is a fast developing area, and we're delighted and honored to be part of this institute because we can't do this work without collaborative interactions. Thank you very much for coming and listening.